To complete our description of LeNet, we need to specify the loss of the network, that is, the criterion which is optimized during the training. Let us denote by f theta xj the output of the jth neuron in the output layer, which is given by the square norm of the difference between the output of the penultimate layer and the prespecified vector wj. The error associated to one observation x, y is given by E theta defined as follows. Note that the first term is composed of one non-zero term only, which corresponds to the output of the neuron indexed by the true label y. We want this term, f theta xj, to be small because we want the vector produced by the previous layer to be close to the stylized vector wy. The second term acts as a regularization since it forces the outputs of the neuron of the previous layer to be far from the stylized vector wj. The minimization of the global expression leads to a small value for f theta xy with large values for the other components of f theta x. A question for you now: do you recognize the expression of the error of the network? You can see with the sum of exponential that it is closely related to the softmax output function. Indeed, you can rewrite this expression as below. If we choose for the constant c a very large value, then exponential minus c is going to be really close to 0, and this quantity is really close to the negative log likelihood of a softmax output layer. To put it differently, this expression is really close to the cross-entropy loss of the network, for which the last layer is the softmax output layer. Here is the update equation of the optimization procedure, which resembles a gradient descent procedure. Indeed, eta can be seen as a learning rate, mu is a numeric constant used to prevent the denominator from being close to 0, and hjj is a diagonal element of the Hessian matrix associated to ei. As we have seen in the optimization course, the matrix H is quite complicated to compute since theta j appears in different connections because of weight sharing due to convolutional layers. We can still rewrite hjj in this form, but this quantity is complicated to evaluate correctly. Instead, an approximation of each diagonal term hjj is performed at the beginning of each epoch using the first 500 observations only, the whole dataset being composed of 60,000 observations. Since computing exactly the Hessian matrix is quite computationally intensive, we compute the Hessian matrix only once at the beginning of each epoch. The whole optimization procedure works as follows. You initialize each weight with a uniform distribution where the variance depends on 1 over the square number of inputs of the unit the weight belongs to. The idea is to keep the weighted sum in the same range for each unit. This should remind you of some initialization we have seen in the previous course. If not, feel free to watch the dedicated sequence again. After the initialization, we update the weights theta j as follows, where I is a randomly chosen index and hjj is computed at the beginning of each epoch. The optimization lasts 20 epochs, where eta is decreased through the epochs in this way. It is really important to tune the value of eta during the optimization process for the network to converge. Here are some classification results for this network. Here are displayed 82 misclassified images by the previous network. For each image, you can see the correct answer on the left and the prediction on the right. Most errors are either caused by genuinely ambiguous patterns or by digits written in a style which is not present in the training set. When you deal with images, it is always interesting to plot the prediction and the true labels in order to detect a possible pattern in the errors of the network. You can also compute the confusion matrix to have a quantitative information. Plotting images and predictions allows you to roughly assess the difficulty of the problem. Here, some digits are not well written. Even for a human, it would be quite complicated to classify some of these images. So maybe there exists no algorithm able to do a better job than this one due to the intrinsic difficulty of the problem. We are going to see in the sequel more complicated algorithms for handling more complicated images.